So let's just look at this more from a chemistry standpoint. How are acids and bases defined? There's different definitions. The Arrhenius definition, named after the scientist who discovered this or came up with this, says that an acid produces hydrogen ions in aqueous solution. So if you take a substance and you dissolve it in water and it produces hydrogen ions, it is an acid. We learned how to name and classify some compounds as acids, and all of those fall into this definition of Arrhenius acid, such as HCl. So it starts with H, right? This is a covalent compound. It does not contain ions. It's two nonmetals. It's a covalent compound. We name it as an acid. But when you put this into water, it ionizes. It forms ions. It forms hydrogen ions and chloride ions. Because it forms hydrogen ions, it's an Arrhenius acid. Hydrogen ions are very reactive. Let's think about what is a hydrogen ion. A hydrogen atom has one proton and one electron. To become an H plus ion, what happens? You remove the electron. What's left? Just a proton. So we've got this proton, and it does not like being out there all by itself. So it's going to react with anything it can. So this is occurring in aqueous solution. There are water molecules everywhere. So this hydrogen ion, this proton, does not like being off by itself. So it is going to react with a water molecule. The water molecule has two lone pairs here. This hydrogen is seeking a duet of electrons. It has none. So it will form what's called a coordinate covalent bond with water, where water is sharing both of the electrons with hydrogen. Hydrogen didn't bring any in. It's like a total charity case, right? This oxygen is like feeling very generous. I'm going to share one of my lone pairs with you so that you can feel like you have a duet of electrons. And that makes this ion, H3O, with a positive charge. And that has the special name hydronium ion. Hydrogen ions are not actually found by themselves in water. As soon as they are formed, they will react with a water molecule and form hydronium. We often talk about H plus aqueous, hydrogen ions, but what we really mean is H3O plus. It's just that talking about the H plus makes all the formulas and equations and things much simpler, but we understand that the hydrogen ion is not by itself. It's riding on a water molecule. So I think of hydrogen ions as being very, very small humans, like, infants, can't walk, right? They are dependent on adults. So here's water acting sort of as a babysitter or a parent and carrying this little one around. You go to Disneyland, you don't see 3-month-old babies waiting in line by themselves, right? They're not like laying on the sidewalk. It just doesn't happen. If one was on the sidewalk, somebody would pick it up and try to find the parent or who it belongs to, right? So we don't actually find hydrogen ions by themselves. They're all being carried around by water molecules. When we write the molecular formula for an acid, we learned that we write the hydrogen first and then the rest of it. Well, we have to talk about some organic acids, and we didn't learn how to name these, but we should recognize them. So this is an acid, HCHO2. Here's its chemical structural formula. This H is written first because that's the hydrogen that comes off when this dissolves in water. It's an acid. When it dissolves in water, the hydrogen ion comes off. So this one is written first. This hydrogen does not become an ion and leave. It sticks around. So we always write ionizable hydrogens first and the rest of them back with the other ones. So here's the structure. This hydrogen that's bonded to the oxygen is the one that will become an ion and leave. This hydrogen bonded to the carbon is going to stay put. So that's why we sometimes write things a little strangely. What is a base? Well, the Arrhenius definition of a base is something that produces hydroxide ions in aqueous solutions. So you put it into water and it forms hydroxide ions. So sodium hydroxide is a base it's an ionic compound with sodium ions and hydroxide ions. It dissolves in water and it forms hydroxide ions. Not everything that has OH in its formula is a base, though. Something like methanol, CH3OH, that's got OH in it, but it's not a base, because this is a molecular compound. It's not going to form ions. It's not an acid either. It doesn't have an H at the beginning. So for our purposes, a base is a metal hydroxide. Sodium hydroxide, potassium hydroxide, something like that. An acid, which produces hydrogen ions, and a base, which produces hydroxide ions, will form water. The hydrogen ion from the acid will react with the hydroxide ion from the base and form a water molecule. They neutralize each other then. The Arrhenius definition is simple, but it doesn't cover everything. There are some substances that act as bases even though they don't have hydroxide in them. And the Arrhenius definition doesn't work if you've got a solvent other than water. So enter the Bronsted-Lowry definition, named for two scientists. Here, an acid is a proton donor, a base is a proton acceptor. So this will define acids and bases that were defined such as under the Arrhenius definition. It'll still include those, but it'll also catch some other ones. Let's think about it. The proton, right? A proton is a hydrogen ion. So an acid donates protons. So you put the acid in water, and it donates a hydrogen ion, a proton, to something else. What is that something else? Well, what did those hydrogen ions do? They reacted with the water around them, right? So here we're focusing on transfer of hydrogen ions from one to another. So here's HCl, not an ionic compound, but when we put this into water, it forms hydrogen ions and chloride ions. The hydrogen ion does not like to be by itself, and so it's going to jump onto the nearest water molecule, forming a hydronium ion. And then we've got the chloride left. So here, this is the acid. It donated a hydrogen ion to the water. The water accepted the hydrogen ion. It accepted the proton. A proton acceptor is a base. So I think of bases as being like babysitters. So you're at Disneyland and you've got your baby with you and you want to ride the Matterhorn and they won't let the baby on the Matterhorn. So you have someone else hold your baby while you go and ride the ride. So you donate, you hand off the proton to someone who's going to hold it for you. They accept the proton. So this is the base, like the babysitter. Base, babysitter, accepts the proton. This is the parent donating or handing off. Ammonia is a base, but it doesn't have hydroxide ions in it. When we put it in water, it does form hydroxide ions, but the Arrhenius definition does not explain how this is going on, what's going on here. So here, NH3 reacting with water, the water donates a hydrogen ion to the ammonia. The ammonia accepts the hydrogen ion. The ammonia is the base, the babysitter. So the ammonia accepts the hydrogen ion. When you put an H plus on this, you get NH4, the ammonium ion. Here, water has donated a hydrogen ion to something else, Water is acting as an acid. So ammonia is a base. It forms hydroxide ions in solution by accepting a hydrogen ion from water. Acids and bases always go together. So when you put this HCl into the water, in order for this to be an acid, it has to donate a proton. It cannot donate a proton unless there's someone there to accept it. You can't leave the baby in the line and just take off, right? You have to hand it off to someone. So there has to be something there to accept it. So the HCl is the acid, the proton donor. Water is the base, the proton acceptor. When ammonia is in water, ammonia is the base. It accepts the proton from water. So water can act as a base or as an acid. Very, very versatile. We have a word for that, amphoteric. An amphoteric substance can act as an acid or as a base. Like an amphibian can live in the water or on land. It lives in both, right? It goes back and forth. So water, an amphoteric substance, can act as a base or as an acid. Now, if we take the equation, this one, where we had ammonia and water, and we formed ammonium and hydroxide ion, notice that there's a double-headed arrow here. This is a single arrow. This is going to go forward and just be done. This one will go in both directions. It establishes an equilibrium. So if we write this equation exactly backwards, let's look at what's happening. So all we did was switch the reactants and products. Here we have ammonium ion reacting with hydroxide ion to form ammonia and water. And what's happening when that happens? What's occurring? Well, NH4 plus is donating a hydrogen ion to the hydroxide to form ammonia and water. So ammonium is acting as the acid, hydroxide is acting as the base, accepting the hydrogen ion. So ammonia acts as a base, ammonium acts as an acid. They're referred to as a conjugate acid-base pair. They are related simply by a hydrogen ion. One has the hydrogen ion, the other does not. One can donate a hydrogen ion, the other could accept a hydrogen ion. So conjugate acid-base pair, any two substances related to each other by the transfer of a proton. So we need to be able to identify these. The way you identify these is you look at the two formulas, and if the difference is just an H+, then you know that that's a conjugate acid-base pair. So we look at these two formulas, NH3, NH4+. So we can get from this one to that one by adding H+. We can get from this one to that one by subtracting H+. Water and hydroxide are a conjugate acid-base pair. To go from H2O to OH-, you just remove a hydrogen ion. If you want to get water from hydroxide, you add a hydrogen ion. So they're a conjugate acid-base pair. Anytime that you have an acid and a base reacting, you're going to form the conjugate acid and conjugate base. So here's the base. When it acts as a base and accepts a proton, it becomes an acid. Here, water's acting as the acid, donating the hydrogen. It becomes a base because it donated the hydrogen. Now, it could take the hydrogen back. So let's look at these and identify the acid and the base, the conjugate acid and the conjugate base. The conjugate acid and conjugate base are always going to be in the products. So what we're going to do here is we're going to look at the formulas. Here, this is C5H5N, and this one is similar, but this is C5H5NH, and the overall charge is plus. So when this became that, did it gain a hydrogen ion or lose a hydrogen ion? It gained. it's a hydrogen ion acceptor. This is the acceptor. Is that the acid or the base? It's the babysitter, right? It's taking the baby. So it's the base. So this is the base. And we can look at the other two things here, the other reactant and the other product. How did H2O become OH minus? By losing a hydrogen ion. It donated a hydrogen ion. So this is the acid. The acid donates a hydrogen ion to the base. This one's the base. The one in the products that's very similar to it, just differing by an H plus, is the conjugate acid. So this is the conjugate acid. Because by accepting the hydrogen ion, it becomes an acid. This one is then the conjugate base. Any questions? Okay, down here, which of these is the acid? Which is acting as a hydrogen ion donor? HNO3 or H2O? HNO3. This is losing a hydrogen ion. HNO3 becomes NO3 minus. So if this is the acid, what's this one? The conjugate base. I'm going to call it CB, conjugate base. This one's the acid, this one must be the base, right? So here's the base. And did this accept a proton? Yes, it did. It accepts the proton, and now it becomes the conjugate acid. So the acid is the thing that's holding the baby, the proton. The base is the one that could take it off their hands. When you hand the baby to the base becomes an acid. The acid becomes a base. Not confusing at all, right?